Okay, let's get started. Let's get started on the topic for today. So today we're going to be talking about non-parametric few-shot learning. This will also be part of your second homework assignment. We'll talk about a few different methods for this and what non-parametric few-shot learning even is. And then we'll also go over a case study of applying a form of non-parametric few-shot learner to a medical image diagnosis problem. After that, we'll talk about some properties of meta-learning algorithms that are desirable, and we'll compare the three different classes of approaches we've talked about so far with respect to those desirable properties. And then we'll also go over a few meta-learning applications, including imitation learning, drug discovery, motion prediction, and language generation, and cover some of the ways that people have applied ideas in meta-learning to various problems. And then by the end of the lecture, hopefully you'll be able to understand non-parametric few-shot learning techniques as well as how to implement them, which will be helpful for your second homework. We'll go over kind of the trade-offs between different kinds of methods. And then also I hope to give you some familiarity with different applied formulations of meta-learning as well. Okay, so that's the plan for today. And before we kind of talk about non-parametric few-shot learning, I want to just briefly recap the two classes of meta-learning approaches that we've talked about so far. So last week we first talked about black box meta-learning, and the key idea with a black box meta-learner is that you have some set of training data points that's going to be fed into a black box neural network, such as a recurrent neural network F theta. And you'll also additionally pass in a new unlabeled test input and train this entire learner to be able to correctly predict the corresponding label. And this is also the kind of meta-learner that you've been implementing in homework 1. And the benefits of this is it's very expressive. The downside is that it's a very challenging optimization problem, which you may have encountered in the homework as well. Next, on Wednesday last week, we talked about optimization-based meta-learning, which embeds an optimization inside this meta-learning process, and then you can differentiate and optimize things such as the initialization of that optimization process, the learning rate, and other free parameters of the optimization. And this is kind of the main benefit of this kind of method is that it builds in the structure of optimization into the meta-learning process, which can make it easier to optimize and also easier to generalize to tasks outside of your task distribution. The downside is that it typically requires a second order optimization, which may be computationally expensive. Okay, so these are the two meta-learning algorithms that we've talked about so far. And what we're going to talk about today is if we can embed a learning procedure into the meta-learner without requiring a second order optimization. And in particular, so far we've been thinking about learning parametric models and kind of parametric approaches to learning. But when you're in a low data regime, non-parametric methods are simple and they actually work quite well in the low data regime. So for example, things like nearest neighbors is an example of a non-parametric approach to learning, where you have some data and you take whatever kind of training data point is closest to your test data point, you output the corresponding classification. And there are, of course, variants such as k-nearest neighbors and so forth. And one kind of critical thing to note is that in the kind of few-shot meta-learning problem that we've been talking about, at meta-test time, few-shot learning is exactly in the low data regime. So kind of with this in mind, we want to think about how we might leverage non-parametric methods in the inner loop. However, during meta training, we still want to be parametric because we want to be able to leverage a large amount of previous experience and data. So kind of the key trade-offs between parametric and non-parametric methods is that non-parametric methods are simple and work well in the low data regime, but when you have a ton of data, they don't scale as well because you have to kind of do lookups on your training data set. And so that's why kind of when we're doing few-shot learning at meta-test time, we're going to look at being in the non-parametric setting, and during meta training, we're going to try to be in the parametric setting. And in particular, kind of the key idea is whether we can use parametric meta-learners that produce effective non-parametric learners. So that's the motivation here. Do you have a question?
Yeah, can you please recap as in what is parametric and what is non-parametric learner?
Yeah, so a parametric learner is a setting where you are you're learning a model, a parametric model that has parameters, hence the name parametric, that, for example, like a classifier that takes as input an input and produces an output. And in non-parametric methods like nearest neighbors and k-nearest neighbors, there's no parameters involved because, and essentially kind of your training data points are kind of like your parameters. Your data is like your parameters. So in this diagram, which is showing an example of nearest neighbors, each of these blue and red points are the data points in your data set. And whenever you want to classify a new data point, you basically just look at the color of that corresponding spot. So if your new data point is somewhere over here, then it would be blue because the nearest data point is blue. If you're somewhere over here, then you would output the label red because the nearest data points are red. And in this sort of approach, there's kind of no parameters, which is kind of why they're called non-parametric methods. Okay. Cool. And I guess it's also worth noting that some of the methods that we'll be covering today actually precede some of the parametric approaches to meta learning. Okay, so how do we actually do this and what does this actually look like in the few-shot learning setting? So if you were to take our classic like few-shot image classification problem and apply it a non-parametric learning technique like nearest neighbors, what we would do is we would take our test data point and compare it to each of the training points in our data set, and then find the nearest neighbor and output the label corresponding to the nearest neighbor. So if this image was the nearest neighbor, then we would output the class corresponding to this image. If this one was the nearest neighbor, we'd output the other corresponding class. Now, so the idea is that we're going to be comparing our test image with our training images. Now, an important question here is in what space do you compare, and with what distance metric do you compare? So one kind of very naive and simple idea that we might do is maybe do like L2 distance in pixel space to compare images. And that's what like a typical kind of naive nearest neighbors approach would do. But unfortunately, this is a pretty bad idea. So for example, this is a example from this paper by Richard Zhang et al., where if you took this image and compared it to these two images, you would think intuitively that it should be closer to this image just because that kind of perceptually looks more similar. But if you actually compute the L2 distance between these two images, it turns out that this one is actually closer in L2 distance than this one. So this suggests that this is kind of one anecdotal example of why L2 distance might be a bad idea. Okay, so what might we do instead of doing pixel space or L2 distance? Does anyone have any ideas or thoughts or thoughts on what we might do to get a good distance metric? You can raise your hand or enter it in chat.
Yeah, maybe you can learn some sort of embedding heuristic, and then I guess sort of like features that would already be extracted in like a CNN, and use that like embedding in the feature space to compare.
Yeah, so one thing you could do is instead of doing like distance in the original space, you could do it in some embedding space. And this will likely produce kind of a much better distance metric if that embedding reflects kind of more the semantics of these images. Any thoughts on where you might get that embedding, either from someone else?
Professor?
Yeah.
So maybe I'm thinking we can take the pre-trained model, for example, like the ImageNet pre-trained on Resin 50 and take maybe the first layer or second hidden layer and just to feed through the image that I want to compare and take out the like second or some intermediate hidden layers and use that as embedding.
Mm-hmm. Yeah, so you could basically train a model on ImageNet and use the kind of embeddings produced by ImageNet and do nearest neighbors in that space. So that's kind of one way that you could get such embeddings. Are there any ideas for how you might kind of use a meta-learning-like approach to get an embedding? Or a distance metric?
Perhaps you could have a model which feeds over each of the images and produces some embedding. You perform the distance measure over that embedding, and then the loss is used to train that model's the embeddings that it produces.
Yeah, so this, I think that you're kind of getting at the right idea. Does anyone want to elaborate on that? Maybe.
I'm thinking we can train a model to directly predict whether two images belongs to the same class. So the output would be directly the distance metric.
Yeah, so that's actually the first approach that we'll talk about, which is that you can basically train something to compare images and tell you whether or not those images are from the same class. And so we can basically use the meta training data and learn this comparator that tells us if something is the same or not. So what this looks like is, for example, you could train a Siamese network to predict whether two images are of the same class. What this would look like is you take two images, you pass that through a network to produce kind of an embedding, and then you have kind of an additional set of layers that output whether or not they are the same class or not. So for this pair, you would train it to output 0 because they're a different class. For this pair of images, you would tell it to output 1 because these both correspond, to the class of bowls. Looks like the slide isn't advancing on. Yeah, so in this case, you would train it to output 1. In this case, you would train it to output 0. In this case, you would train it to output 1, and so forth. So essentially, you're kind of training a network with your meta-training data to tell you whether or not two images are from the same class. And then at meta test time, when you want to predict the label, what you can do is you can compare each, you compare your X test image to each of the images in dtrain and predict the label corresponding to the image that has the highest probability of corresponding to the same class as your test image. Cool. So this is kind of like the first, this was actually an approach proposed in 2015, and it was really one of the first approaches to using neural networks in the context of few-shot learning. Any questions on that? I feel like I'm also behind on the chat. I think the chat was mostly thinking about questions from, or answers to the previous questions. So do you have a question?
Yes, so when we're thinking about non-parametric, because the neural network has like parameters, is that like kind of like not counted in this case? Like maybe if you can, I was a bit confused.
Yeah, so I guess I'm calling this kind of a class of non-parametric methods or learners in the sense that there are actually parameters, and these parameters are actually trained with the meta training set. I guess it's, I like to call it a kind of a non-parametric method in the sense that it really resembles a lot of the non-parametric methods that we have in machine learning, like nearest neighbors, k-nearest neighbors, and so forth, because we are kind of just looking at the images and literally, like in this case, literally doing nearest neighbors, but according to this meta-learned metric of whether or not two images are the same. So essentially you can view it as like a parametric meta-learner that's kind of giving you a metric under which to compare images. And then once you have this metric, you're using kind of a non-parametric approach to predict the label for the test input.
Oh, okay. So the non-parametric aspect of it is where we actually predict it from just like this final level of state.
Yeah. So you can sort of view it as like the inner loop being non-parametric and the outer loop being parametric. Of course, the model that the outer loop produces is used in the inner loop. So it potentially could be viewed as like a semi-parametric approach, but I think you have the idea.
Okay, cool, thanks.
Yeah, and so asking, the distance layer uses a specific metric, or does it learn metrics from the training data? So in this case, this network here, which is essentially kind of learning a sort of metric, although it may not kind of obey the triangle inequality, but in any case is learning something that makes comparisons between these two images. And we train this network using all of the meta-training data, all of the image classes in our meta-training data. And then when we're given new image classes, we can still expect this model to generalize because it's simply telling you for a new pair of images whether or not they're the same class. And you follow this kind of procedure down here to make a prediction for X test at meta test time. Okay, so this is kind of the key idea behind this initial approach. Now, in general, this approach works pretty well, and it's quite simple, which is really nice. But one downside of this approach is that during meta training time, you're basically training it for this binary classification problem of whether or not these two images are the same class. But at meta test time, you're doing this n-way classification where you're comparing the images, the test image to all of the images in the training data set and outputting the corresponding label within the n classes. And so we have this discrepancy between what we're meta training for and what we're meta testing for. So one thing that we would like to do to improve this approach is to try to match what's happening at meta training time and meta testing time. So this is kind of the key idea behind this work called matching networks. And essentially, you could view it as learning an embedding space and doing nearest neighbors in that embedding space, and then optimizing for a model such that nearest neighbors outputs the correct answer. So what this looks like is something like this, where all the images on the left are the training data points for your task, and this is the test input, X test. You pass all of these examples in. You basically get embeddings for each of your training examples. You also get an embedding for your test example. And then this operation computes something like the kind of negative distance between your test embedding and each of your training embeddings. And then once you kind of have compared these and kind of have an estimate for which of these is the most similar to your test example, you then use this to use this estimate and dot product it with the labels of each of your training examples to produce the corresponding label. So for example, in this one, when you compare the embedding of the dog here and the embedding of the test example, it finds that that is kind of has the highest weight or is the most likely to match. And then when you take the dot product, it will output the corresponding label for that dog because that has or for the red label because that has the closest image. So kind of mathematically what this looks like is you can view each of these black dots as this function that tells you the similarity between X test and each of your training examples XK. These are each of the labels YK for each of your training examples. And then your output Y hat test is basically equal to the kind of dot product between your similarities and your labels. So you can essentially view these similarities as probabilities over which example it thinks it is. And once you take these probabilities and output it by the corresponding label, you then get a probability distribution over what you think is the label for this test example. Cool. And then I guess I don't want to go into the architecture too much, but a couple kind of general things about this architecture is that it uses a convolutional encoder to embed the images into these vectors. And for the embeddings of the training examples, it actually isn't just a feed-forward model. They actually use a bidirectional LSTM. So the embeddings of each example is actually also affected by the other images in the training data set. And this whole architecture is trained end to end with respect to the accuracy on your test example. Okay, do you have a question?
Yeah, so for the embedding, do you use a pre-trained model or this is trained end-to-end?
It's all trained end to end. You could kind of pre-train some of these modules with like ImageNet or something, but all of it is trained end to end with respect to the few shot classification prediction here. It also looks like there's a question in the chat saying how is H theta and G theta related? I think that they're just kind of denoting these as basically theta are the parameters of the entire MetaLearner, and these are just kind of two completely separate models that use different parts of theta to make their corresponding prediction. You have a question?
Yeah, just want to know in the G of theta part, which network comes first? The LSTM comes first or the CNN?
I think it's a convolution. I think they first kind of use a CNN and then they do a bidirectional LSTM on top of what the convolution layers produce. You can check the paper for details.
Do you have any intuition behind this?
Yeah, so LSTMs typically operate on like kind of low dimensional vectors. And so if you took like the standard LSTM and applied it on top of the images, you actually need to flatten the images before passing it into the LSTM, which wouldn't leverage the spatial structure of the image. So that's kind of one reason why it may make sense to put the convolutions first. That said, there is an architecture, there's kind of a version of an LSTM called a conv LSTM that basically replaces all the matrix multiplies with convolution operations. And you could imagine doing something like that instead of doing convolution and then LSTM.
Yeah, thank you.
Okay.
Yeah, this looks a lot like an attention mechanism in a lot of ways. So I'm curious how well in practice this really generalizes to unseen data, and how much it's just learning things like, for this example, features endemic to dogs.
Yeah. Let's see. So it does actually draw a lot of similarities to attention. This was back in 2016, and I don't even know if attention had really been really thoroughly defined or wasn't very popular, at least at that point. And maybe if this paper was introduced today, they would have called it something more like attention. This operation right here, certainly in particular, looks a lot like attention because you're kind of comparing the embedding to each of the other embeddings. In general, it does actually generalize. These kinds of architectures do actually usually generalize pretty well. In practice, I think because of kind of the structure that's built in. We'll also introduce one more approach that builds upon this idea that is kind of one of the more, I think, de facto models in kind of the non-parametric few shot classification realm. It also looks like it's asking, are H theta and G theta the same network or different? These are kind of different networks. And this particular is just kind of a feed-forward convolution model. And this model is a bidirectional LSTM. I think that there are some weights between this convolutional encoder and kind of the encoder of this one, but I can't remember exactly. You can check the paper for details. Okay. Cool. And then is asking, what are the drawbacks of letting them share the same network? I think that there are benefits to parameter sharing in general because it may increase the efficiency. It may also be that it's helpful to have a different encoder for the training examples than for the test examples. For things like edge detectors, then parameter sharing makes a lot of sense, but maybe there's some other features that it may want to encode differently in the training examples and the test example. And I'll take one more question from.
Hi, so is this still going to be trained in like a two process where you backpropagate the performance on the meta test set, or like the query part of each task in the meta train set?
Yeah, so basically you'll still, well, we'll go over the full procedure, but you will backpropagate and train all of this with respect to how accurate Y hat test is, basically how accurate it is able to classify this test image.
Cool, thanks.
Cool. And then I guess one thing to highlight here is, unlike Siamese networks, now meta-training and meta-testing match, because you're actually meta-training it for kind of n-way classification, whereas Siamese networks is just training it for two-way classification. What the algorithm looks like is basically pretty similar to the kind of general framework that we've gone through before. What's going to be a bit different is, instead of computing these parameters, we're going to be computing the prediction for the test input. This kind of illustrates how it's somewhat of a non-parametric approach. We're not actually computing any parameters of any model. We compute the prediction on the test input. You can also view this as having the parameters sort of integrated out. And then we'll update the kind of meta parameters of this overall model using the prediction error on your test inputs. Okay. Great. So this is what we just talked about is called matching networks. It's a pretty popular approach for few-shot learning. Now, when we think about kind of one more approach that builds upon this, one important question to think about is, what if you have more than one shot? What if you have more than one example per class? And in particular, if we go back to this architecture, does anyone have any ideas for like what you might do with this architecture, or kind of how this architecture handles the case where you have more than one example per class? So maybe you have two dogs of this breed, for example. How do you think that this model handles that case? Yeah, so is asking, take the sum of all examples. So one thing that you could do is instead of, so basically when you have two examples of this dog, this embedding, for example, you could have just kind of one embedding for that kind of breed. This is actually hinting at what we'll talk about in the next approach. In this matching networks paper, though, the way that they handled the setting where you had more than one examples is it just treated them completely independently. So it just took, if you had two examples of this other dog, it would also pass that kind of the example of that dog breed, create another embedding vector for that dog breed. So it had two embeddings for that label, and then it added kind of an additional label here. And it would basically treat them like independently, almost as if they were different classes. So this is kind of the approach that Thing is mentioning, where you just basically feed all the images in and also feed all the corresponding labels, and you don't do anything special to aggregate information across a class. And this is kind of potentially a bit of a downside, because it doesn't really aggregate class information across images. And the aggregated information may be more useful, because maybe kind of the test examples you'll see may have features present in one example and some features present in another example. And if you don't aggregate that information, it may not be able to accurately predict the label for that test example. And so this is kind of the key idea behind what's called prototypical networks. And what it does is each of these colored dots corresponds to the different examples in dtrain, embedded into a kind of a low-dimensional space. And instead of treating kind of these examples completely independently, which is what matching networks would do, it takes the average of all of the examples of the same class. And then when it does nearest neighbors, instead of doing nearest neighbors to kind of each of these, it does nearest neighbors to the prototypical embedding of each of those classes. So all these green examples correspond to C1, all the blue examples correspond to C3, and so forth. And you average the embeddings to create a kind of a prototypical embedding for that class, and then do nearest neighbors with regard to the prototypical embedding. So mathematically, what this looks like is you compute each of these centroids, Cn, by averaging all of the embeddings for the data points in that class. Basically, for all the embeddings with the label equal to n. And then when you want to compute the label for a new test input x. You then look at the distance between your test example and each of these centroids. And then to get a probability, you exponentiate the negative distance and then normalize. Okay, and then this distance function d, it could be, in this paper, they looked at a Euclidean distance or a cosine distance. There are other kind of metrics that you could use as well. Crucially, though, this distance metric is inside this embedding space. It's not in the original space. Okay, any questions on how this works? Do you have a question, or is your hand up from before? Okay, sounds good. I'll take that as that was clear, hopefully. What's your question?
Yeah, just curious about how this method compared to previous methods. Other non-parametric methods.
Yeah, so this model was able to show improvements over matching networks, particularly in the case where you have more than one shot. If you only have one shot, then they are basically the same. Because the embedding will be the same as it'll just be that one example's embedding. It also shows improvements, significant improvements. Both matching networks and prototypical networks show significant improvements over Siamese networks.
Yeah, I was just curious if people have tried better strategies than averaging the embedding from training set.
Yeah. So this kind of gets actually at my next point, which is that maybe averaging isn't really the best way to look at things. And what if you have more complex relationships between different data points of the same class? And there are a few different approaches that do this. So for example, I guess this isn't really replacing the average, but this is learning a distance in prototypical networks rather than using Euclidean or cosine distance or something. It's actually learning a neural network to produce the distance. In general, I think that averaging is a reasonable choice because oftentimes the encoder of these embeddings is already doing something more sophisticated than just a feed-forward model. It may already, for example, if it's a bidirectional LSTM, it's already taking into account some of the differences between these images when it produces the embedding space. So typically just averaging, I think, is pretty reasonable, although you may want to learn. One setting where averaging may not work is if you have pretty diverse variation within a class. So maybe, for example, if you're in the, let's see, what's a good example of this? Maybe if your your class is is this a person or an animal, maybe people look very different. And so you may want to have different representations of things, or maybe animals look very different. And so you may want to have different multiple prototypes for different kinds of a more coarse class. And so this paper allows you to learn a mixture of prototypes for each class rather than just having a single prototype. So this is an alternative to just using averaging. And then a third approach is to if you have even more complex relationships between the different classes, there's also another approach that uses graph convolutions to essentially do message passing on the embeddings, where you have a set of embeddings and then you pass messages loosely between those different embeddings to refine your representation of each class. What's your question?
So does it make sense to learn the distance embedding also when the input has a bimodal or multimodal distribution, because the average may not be the main of any of these modes?
Yeah, so I view there as being two design choices. One is how do you, when you have a set of embeddings for all the examples in your class, how do you choose the prototypes? And one way might be to have multiple prototypes using a mixture. And then the second question is how do you derive your distance function? And this method derives learns the distance function in prototypical networks. And you could also combine these two ideas. I can't remember exactly what distance function they used here. It looks like it's just something like Euclidean, for example, with respect to each of the prototype centers. So I think that both of those are kind of design choices that come up in these methods.
The third approach is more like a graph network, right? Graph convolution. What they're learning this distance metric here.
Yeah. And then you asked in the chat, here it seems the embeddings from the same class cluster together. Is that the general case? So yeah, so in the slide that I was showing before, in general, they'll kind of cluster together in your embedding space because that's kind of the right thing to do. But in applications like the ones right here, they may not cluster together. And that in those kinds of situations, if you have a more multimodal distribution within a class, it may make sense to have multiple prototypes within that class. Okay, cool. So now let's move on and talk about how we might look at this, apply these methods to a practical problem. And in particular, we'll look at this paper, which uses a variant on Prototypical that works for dermatological image classification. And this paper appeared at the Machine Learning for Healthcare conference in 2019, and also the NeurIPS Machine Learning for Healthcare workshop in 2018. And there's also a link to the paper if you're interested in looking at it yourself. And the problem that they wanted to look at was few-shot learning for diagnosing different dermatological diseases, so different skin conditions. And this problem has a number of different challenges. So first, it tends to be pretty hard to get data because the data is fairly personal. And also the data is quite long-tailed. So there's a lot of different conditions that are very common, and there are some skin conditions that are very rare. And then lastly, there's also significant intra-class variability. So depending on where the skin condition is occurring on the skin, or depending on the kind of the skin type and so forth, you may have a lot of variability within a single disease. And then the goal of this paper was to try to acquire an accurate classifier on all classes. So essentially different classes are going to correspond to different diseases, and they want to be able to classify which disease a condition corresponds to, which disease a patch of skin corresponds to among all of the classes in their training data set. And in particular, they looked at the DermNet data set, which is visualized here. And in particular, what this is showing is that this is showing that only the top 200 classes where you see this really long tail distribution where for some of the classes like eczema and acne, there's a very large number of examples with like maybe 1,000 or 500 examples. And then there's this hugely long tail where there's many, many conditions that have like less than 50 examples, for example. And there's actually more classes. I think that there's maybe up to 600 classes total in this data set. And even when you only look at the first 200 classes, you still see this pretty dramatic tail. And beyond kind of dermatology, these sorts of long-tailed distributions come up all the time. So this is a problem that's quite relevant in practical machine learning applications. Okay, so their goal was to acquire basically a 200-way classifier for these different diseases. And the way that they formulated this is that different image classes correspond to different diseases. And they took 150 base classes that they're going to use for meta training and 50 novel classes that they're going to hold out and try to be able to generalize to just from a small amount of data. And in particular, they took the base classes are the ones with the most data, and the novel classes are the ones where you only have a small number of examples, which is kind of a natural way to split the data. And then at meta test time, they wanted to get a classifier that can classify among all 200 classes. So unlike the omniglot setting that you're looking at in your homework, where you were like doing like 10-way classification, for example, here they're actually going to be meta training with around kind of leveraging data from 150 base classes, and they actually want a classifier that can go beyond 150 base classes. And now one thing that's worth noting here is that kind of unlike the approaches that we've seen so far with black box and optimization-based meta learning, non-parametric methods can actually train for n-way classification and test for greater than n-way classification, because you can still compute embeddings for all of the examples, and you can still do this form of nearest neighbors or kind of nearest neighbors to the prototypes for more than n, even if you've only trained on n. So this is one of the kind of positive features of these kinds of approaches. So that means that they could actually get a 200-way classifier after only meta-training on a number of classes that's less than that. So the approach that they take is they take prototypical networks and they expand on it in two different ways. So first, they learn multiple prototypes per class. So this is pretty similar to one of the papers that I was mentioning before, where they learned a mixture of prototypes. And this allows them to handle interclass variability. And second, they also incorporate unlabeled support examples where they basically support examples where they don't have labels for. For example, the query examples by doing k-means on top of the learned embedding space. And this allows them to kind of leverage these unlabeled examples to better predict the query examples. Okay, and then one side note is that if you do decide to kind of read this paper and look into some of the details, they actually flip the standard notation of k and n in the paper, which is a bit confusing if you read it, but once you understand that they're flipping this, it's hopefully a bit easier to kind of flip in your head if you're used to n-way and k-shot classification. Okay, and then in their evaluation, they compared to standard prototypical networks, which is trained on 150 base classes. It's also pre-trained on ImageNet. With their method, they also pre-trained the prototypical clustering networks on ImageNet as well. They also compared to this kind of fine-tuning approach where they took an ImageNet pre-trained model, they fine-tuned it on n classes where n is varying. N is either going to be 150 or 200. And then they ran 1 nearest neighbors or 3 nearest neighbors in the resulting embedding space. And then lastly, they compared to an ImageNet pre-trained model that's fine-tuned actually on all 200 classes using balancing. And this last method is a pretty strong baseline. It accesses more information during training than both their approach as well as these two baselines. And also, if you want to introduce new classes into your data set, it requires like completely retraining for those new classes. So in some ways, this method is a bit privileged. It has kind of more information and requires more compute than the other methods. And then they evaluated this on mean class accuracy, which is just the average of each of the per class accuracies across the 200 classes. And this treats all of the classes as equal, even if some of the classes have more data than other classes. And they kind of argued that this is a reasonable thing to do in this setting. Okay, is asking, how does the embedding generalize on unseen classes? So basically when you train this encoder across 150 base classes, you're training it to be able to like produce embeddings that are distinguishable within those 150 classes. And then when you're given an unseen class, the hope is that that encoder will also produce a distinguishable embedding for a new class. And if you train on enough classes, you can expect reasonable generalization, assuming that the new unseen classes are not like significantly far from the distribution of images that you saw previously. Okay, so to finish up this kind of case study, these are what the results look like. So the first thing to note here is that their method that incorporates the unlabeled data and also has multiple prototypes per class is able to do significantly better than just vanilla prototypical networks, which is nice. It does better across both the base classes as well as the novel classes that are held out. Second is that their method significantly outperforms, this is at least on the novel classes. So in general, on the novel classes, PCN is able to significantly outperform when you're fine-tuning and then doing nearest neighbors on the fine-tuned embedding. For the base classes, it does similarly and slightly worse, although in terms of the overall accuracy on both base and novel, it's able to do better than this kind of fine-tuning nearest neighbors approach. And then lastly, they found that their kind of prototypical clustering networks is able to do about as well as this kind of strong baseline that's fine-tuning on all 200 classes, even though PCN was only kind of trained on 150 classes. So this is pretty nice in that they're able to do as well as this method without requiring retraining for every new class that you might want to add to this model. Great, and then they also have more visualizations and analysis in the paper.
Yeah, I'm just curious to know, like, this feed-forward, this fine-tuning method where the network sees all the 200 classes, why that had a very low performance on the novel classes? Because in effect, the model has been trained on those classes already, but the performance is like very low compared to the base classes. Like, is there some explanation why that might be the case?
Yeah, so I think that my intuition for that is that basically when you explicitly train for few-shot generalization, which is what meta-learning methods do in general, and also what prototypical networks and PCN does, you're explicitly generalizing it to be able to produce an embedding that can generalize even when that kind of prototype was produced with only a few examples. Whereas it's very likely, I think, that this fine-tuned model is probably overfitting when it only sees a few examples for these novel classes. Each of these novel classes have like less than 50 examples total, so it's probably pretty easy to overfit. And then also PCN introduces a way to leverage unlabeled data, and that may be helping it to perform better than this method, which isn't able to leverage the unlabeled data.
Thank you.
Also asking in the chat, why is the mean class accuracy low, less than 50%? So first, this is kind of a 200-way classification problem. So random performance would be at kind of 1/200, which is, so it is like substantially improving over that at least. I also think that this task is quite a challenging task. The amount of total data points is per class is relatively low. Even the most populous examples had like around 1,000 examples. And once you get to the novel examples, you have a very, very small amount of data that it has to learn from. And so that would explain why these numbers aren't like in the 90s, for example. Okay. Great. And then there was one other question in the chat, that was about non-parametric few-shot learners, which is that can they be effective for text classification? And yeah, so the original matching networks paper actually included experiments on a text classification problem. So I'd encourage you to look at the experiments in that paper if you're interested in that. But they can be effective for text classification is the short answer. Okay, so now let's talk about some of the properties of meta-learning algorithms and compare the 3 different classes of approaches that we've talked about so far. So we've talked about black box methods, optimization-based methods, and non-parametric methods. And the first way that we'll think about comparing them is from the standpoint of a computation graph. And we talked about this perspective before when we were comparing black box methods and optimization-based methods. And we talked about how a black box method is basically directly producing a model that takes as input a training data set and a test input. And an optimization could also be viewed as this computation graph that takes as input a training data set and a test example, but one where it involves this kind of inner loop optimization inside that computation graph, where essentially you run gradient descent on your training example and then use the resulting parameters to make predictions on your test input. But it's still this kind of general computation graph that takes as input a training data set and a test input. Non-parametric methods can also be cast inside this perspective of a computation graph where you have a training data set and test input, and the way that this prediction is produced is using basically comparing the embeddings of your test example and your prototypes. And each of these prototype examples is computed using your training data set. It's computed using kind of the average of all of the classes in that, the average of all the embeddings in that class. So all three of these methods can basically just be viewed as different forms of this function f, where you kind of pass the data set into the model in some way, either by running gradient descent or by looking at nearest neighbors to a prototype, or by just passing it directly into the model. And also, all of them take as input the test example in some way, either by passing it into the model with updated parameters, by comparing it to the prototype, or by just passing it directly into the model. Cool, so this is one perspective of thinking about the differences of these approaches as basically just different ways to ingest data and a test example. And it's also worth noting, again, is that you can mix and match different components of the different computation graphs and get different kinds of methods as well. So, for example, there's one method that both conditions on the data in this way and runs gradient descent. This is one valid approach. There's also an approach that does gradient descent on top of a relational network embedding. So it's kind of somewhat similar to a non-parametric approach and an optimization-based approach. There's also a method that runs MAML but initializes the last layer as a protonet during meta-training. So there's kind of various ways to design this function that takes as input the training data and the test input, and you can leverage different elements of a non-parametric learner, of a gradient-based optimization, and so forth. Okay, so that's the computation graph perspective. And then the second perspective I'd like to provide to think about these classes of methods is from the standpoint of various properties that we might want. So one property that we might want from these models is for them to be very expressive, to be able to process the data in many different ways. Essentially the ability for this function f to represent a range of learning procedures. And this is helpful for scalability and applicability to a wide range of domains, especially if we don't have good ways to do kind of optimization and learning in that setting. The second property that I think is desirable is something that I'll call consistency. And the idea of consistency is that we want the learned learning procedure to be able to improve with more data. Essentially at test time, when you give it new data from a new task, the more data you give it, the better you want it to do, right? That seems like a pretty reasonable thing to ask. And ideally, it would do that regardless of the task that you're giving it and regardless of the meta-training tasks. Even if this task is out of distribution, it would be nice if it can actually improve as you give it more data. And this will, if you have a learning procedure like this will reduce the reliance on the meta-training tasks, and it will also potentially give you better out-of-distribution task performance. And this is something that we can expect when we're actually running an optimization at test time. Okay. And you can also recall kind of the example that we showed before when we looked at out-of-distribution tasks, and we saw that MAML was a bit more robust. And I think that these two properties are pretty important for most applications. Now, how do these different approaches fare on these two metrics? So black box methods have complete expressive power if you have a big enough recurrent neural network, but they aren't consistent. So if you give it more data and you pass in more data into your RNN, at test time, it may not continue to improve. There's nothing to kind of guarantee that it's actually kind of descending on some objective per se. Optimization-based methods, they are consistent. Because you're running gradient descent, in expectation, you can expect your loss to go down and over time with gradient descent. And they are expressive, like we mentioned, like we talked about on Wednesday, although this does require very deep models in order to get the kind of maximal expressive power that you get with a black box learner. And this is for the supervised learning setting. This actually isn't true in the reinforcement learning setting, but there are some details there, and we'll talk about that when we start talking about reinforcement learning. And then lastly, for non-parametric methods, they are quite expressive for most architectures that you use. The expressive power essentially depends on the architecture, and they're also consistent under certain conditions. Basically, as you add more examples, if your metric is properly assigns like zero distance to two examples that are the same or very similar, then you could expect giving it more training data will lead it to be more likely to produce an example that is very close to your test example. Okay, so that's kind of an analysis of these three methods along those two axes. There are also a number of other pros and cons of these methods. So one thing with black box methods is that they're very easy to combine with different learning problems, but it also produces a more challenging optimization. And I think this is getting at a question asked in the chat, which is, what is the convergence rate of different approaches? It's a bit difficult to kind of theoretically analyze the convergence rate of different conditions, especially when you're using neural networks, because it relies on a number of factors, and neural network optimization is in general a complex topic to analyze. But we can at least say, kind of in practice and empirically, we observe that, at least for black box models, we observe that we have a more challenging optimization and likely slower convergence. And we can also say things about optimization based in non-parametric methods, which we'll get to in a second. And as a result, black box methods tend to be data inefficient in terms of the data that's needed for meta training. Okay, for optimization-based methods, we get this positive inductive bias at the start of meta learning because we are embedding an optimization into the meta learner. It also handles varying K and large K well, because you can simply average the gradient across varying numbers of shots that you have. And it's model agnostic in the sense that you don't have to design a particular architecture like you do in a black box method. And then the downside is that it requires a second order optimization, which can require more compute and memory. And then lastly, with non-parametric methods, one really nice benefit is that they're entirely feed forward. This makes them in general kind of computationally fast and easy to optimize and just easy to work with in general. The downside is that it's empirically been observed that they don't generalize to varying K well, although we did actually talk about recently how they can generalize to varying N well. So they can generalize to varying numbers of classes, but not necessarily varying amounts of data per class. Of course, if you have a very large amount of data in the inner loop, they're going to be hard to scale because you have kind of large computation costs for nearest neighbor lookups. And so far, these methods have been limited to classification for the most part. Yeah, and actually, this gets at the chat. The question that just appeared in the chat is, can non-parametric methods be used for regression? In general, they haven't been used for regression so far. Okay, and then lastly, I'll mention that generally, well-tuned versions of these methods generally perform comparably on existing few-shot learning benchmarks. And this may say more about the benchmarks than about the methods themselves. I think that kind of existing few-shot image classification benchmarks don't really get the heart at what's challenging in meta-learning problems. And what method that you might want to use really depends on your use case and how much you care about these positives and these negatives in your particular use case. I guess one thing I would recommend is if you are doing classification and you want to kind of try out one of these approaches, I think that non-parametric methods are probably the easiest to get up and running in practice. But beyond that, I think that there's kind of different trade-offs between different methods. Okay.
Yeah, so my question is, how is the meta-learning methods like black box or optimization-based work for regression tasks? Or because we have to learn a function, right? It's not possible going to be like a few shot, like 5 shot won't be ideal. So what kind of number of example we should start with when a regression task kind of a problem we are working for meta-learning?
Yeah, so for optimization-based is, well, for both these, it's very straightforward to apply them to regression. You just change the outer loss function to be like mean squared error or some other regression loss function. And for mammal or optimization-based meta learners, you will also change the inner loss to be a regression-based loss as well. And beyond that, you're kind of basically done.
So in terms of sample complexity, like does it we have to look at how many samples to have for learning? Like we don't want to select too many samples for learning, like the number of training examples when you're learning a regression task. Like in classical, we can do in classification, we are having 5-shot learning, right? And
yeah.
Give one example, but that's not going to work in a regression problems.
Yeah, you can still do few-shot learning in a regression problem. It really depends on how broad your task distribution is. But actually, in the original mammal paper, for example, we had a regression task where different tasks corresponded to different sinusoid curves. And we basically had a family of sinusoids with varying phase and varying amplitude. So there's basically 2 degrees of freedom within the task family. And it's able to learn with like 5 examples. It basically just has to identify the sine curve from those 5 examples, and then it can actually regress to the correct values of that sine curve from the input.
So every task is just one function, right? That's, I think, different from the classification problems.
Yep.
And second question is like, why is the non-parametric does not generalize as a very large cases? Because maybe the each class has multiple modes, and that might be the problem when we have a large number of K for the non-parametric approach.
Yeah, so the reason why it doesn't scale to very large K is for the same reason that we don't use non-parametric methods with really huge data sets. To make a prediction with a non-parametric method with like nearest neighbors, for example, you have to search over your entire data set. And if you have a very large data set, then you have to search over a large data set. So it's going to be basically O of K. If K is small, that's completely fine. If K is huge, that's more of a challenge. And then asking, I think, a related question is, isn't the challenge with scaling prototypical networks in N and not K, since we can compute the distance from a query vector to centroids and not the distance? Right, okay, so yeah, so this comment is mostly corresponding to things like matching networks. If you use prototypical networks, then you're right in that it actually has to do more with N. If N is very large, then you'll have to do more comparisons to those prototypes. But you can essentially pre-compute the prototypes, which will make it easier to scale to large K. Okay, one more question from.
Yes, I had a question about like the present homework setting, right? So we are using this data set which has around 1600 classes, and each task we sample around 5 classes from it. And then we are assuming at test time in the real world when you're using, we'll also supply like a support set which has a few number of classes, and then we'll use it to predict on a query set. But if we want to learn a model that can predict all the classes or like 500 classes or something like that, then do we continue with the meta learning or the few shot learning setting, because we are still per class we still have a very few examples, right? Or do we then move on to the supervised learning setting? Basically, I'm asking, how do you train a learner that can do many classes but still having not too many examples per class?
Yeah, so that's basically exactly what this case study was looking at, where you wanted not to just, you basically wanted to be able to produce to be able to essentially kind of test on all 200 classes, even if you had only trained on up to 150 classes. And with these non-parametric methods, it's actually quite easy to do this, because for these base classes, you've essentially formed prototypes for these base classes that work well with all of the kind of examples that you have. And then you could form additional prototypes with your novel classes by passing in those few examples and then averaging them to produce an embedding. And then you just basically add in prototypes. And then when you classify among the 200 classes, you consider all 200 prototypes, or kind of, in this specific case, they're actually learning multiple prototypes per class. So it's actually more than 200 prototypes. But it's easy to basically add these prototypes and kind of add them as you get more classes, and then do nearest neighbors to those prototypes.
Thanks.
Great. Cool. So now let's talk about some applications, which is maybe the most fun part. Oh, actually, before we talk about applications, there's one more property that I want to mention, is uncertainty awareness. So one other thing that's nice to have in a meta learner is to reason about ambiguity during learning. If you only have a few examples, then it may not be completely clear what the correct function is, even if you have a lot of previous experience. And it'd be nice to know, like, if the few examples you have is enough for you to make an effective prediction, or if the model thinks it needs more data to be able to make an accurate prediction. This is especially useful in active learning settings where it's possible to get more data in reinforcement learning settings where you can explore in different ways to collect more data. And it's also useful for getting calibrated uncertainty estimates, which might be relevant in safety critical settings where you want to know whether you trust your model to make an accurate prediction. And it also leads to more principled, a more principled interpretation to exactly what these methods are doing within the framework of Bayesian graphical models. Okay, and now let's wrap up by talking about some applications, which I think is always pretty exciting. And I'm just going to go over 4 applications that illustrate some of the things that you can do with meta-learning methods. This is by no means kind of a complete survey of the applications that people have looked at, but can maybe hopefully get a taste for what these methods are capable of doing. So in this first application, the goal is to do imitation learning. And imitation learning is a really powerful framework for training robots and other sequential decision-making systems by just telling them to supervise, basically doing supervised learning with regard to some demonstrations that are provided. But collecting a lot of demonstrations, for example, on a robot is very expensive because it requires a human to teleoperate the robot in a certain way. So in this case, the different tasks correspond to manipulating different objects that you want the robot to be able to manipulate. So for example, different tasks might correspond to different objects that the robot is holding and different containers that you want the robot to place the object into. In this case, dtrain is going to just be a video of a human doing the task. So our goal is to have the robot be able to do kind of one-shot learning from this video of a human, and dtest will correspond to a teleoperated demonstration. And this basically tells it, after you see this training data, these are the actions that you should take to complete the task. And then the model that's used in this work is an optimization-based model. It corresponds to MAML with a learned inner loss function. And the reason why we need to learn this inner loss function is we don't actually have a set of labels in this video of a human. And if you're kind of interested in learning more about that, you can look at the paper. And here's an example of what it's able to accomplish at test time, where a person, in this case, places a peach into this red bowl, then shuffles the objects around, and the robot executes the policy that it learned in one shot. And it can figure out that what it should do is place the peach into the red bowl. Cool, so this is one example of one-shot learning applied to imitation learning. The next application that I'll talk about is low-resource molecular property prediction, where you want to be able to predict the activities and properties of a certain instance of a molecule with only a small amount of data. And this might be quite useful for low-resource drug discovery problems, where basically each data point requires running, actually synthesizing that molecule and running experiments with that molecule. And so different tasks correspond to predicting the properties and activations of different molecules. And dtrain and dtest correspond to different instances, I think, of different molecules and potentially different kind of circumstances. Although it was difficult to find some details on this in the paper. But if you dig a bit further, it might be a little bit more clear exactly what dtrain and dtest correspond to. And then the model in this case is optimization-based. They tried a few different variants of optimization-based models, including MAML, first-order MAML, and almost no inner loop, which basically corresponds to MAML, but where you only update the last layer of the model in the inner loop rather than updating the entire network. And then the base model that they used with MAML was a gated graph neural network so that they could process the molecules. And these are generally the results that they found. They found that in general, mammal was able to do better than first order mammal and animal in each of these cases, and was also able to significantly outperform using k-nearest neighbors and fine tuning on a variety of different held out molecules. So this is pretty cool. The third application that I'll mention is few-shot human motion prediction. And the authors argued that this might be useful for human-robot interaction. I would also suggest that this could be quite useful for autonomous driving. If you wanted to know whether a human will cross the road, for example, or might continue standing at their particular location. Different tasks correspond to different human users and different motions that they're performing. And the training data for each task corresponds to the past k time steps of motion, and the test data corresponds to the future seconds of motion. Essentially, you want to be able to predict the future based on the last kind of snippet of time. In this case, they use kind of a hybrid of an optimization based on a black box method, where they used mammal, where they kind of first fine-tuned with gradient descent, and then additionally used a learned update rule on top of those fine-tuned parameters, and then trained everything end to end. And then their base model was a recurrent neural network. And these are kind of qualitatively what their results look like, where PAML is the kind of their proposed hybrid method. The top is the ground truth. This is the data. This is their kind of detrained data right here. And then this is the prediction forward. And what you can see is that it's able to kind of predict that this person will keep on sitting down, and it's also able to predict the kind of arm motions of the human with relatively decent accuracy. And then they also looked at the kind of mean angle error with respect to the prediction height horizon, ranging from 80 time steps to 1,000 time steps, and are able to find that it kind of performs a lot better than various multitask learning approaches and various transfer learning approaches. Okay, and then the last application that I'll mention is the GPT-3 paper that we didn't quite have time to go through in the lecture on black box meta learning. And in this case, their tasks are quite diverse. It corresponded to things like spelling correction, simple math problems, and translating between languages, and a variety of other tasks, which I think is actually really cool that they're able to train it on such a broad distribution of tasks. And they represented all of these tasks as language generation problems, where kind of detrain corresponds to language that shows kind of the correct answers for some of those problems, and detest corresponds to kind of what the future language should look like. And here's kind of an example of how you can write down simple math functions, spelling correction, and translating between languages, all as this language generation problem. The way that they trained this is they took like a really just large amount of text data from the internet, from books, and other language corpora, and detrain corresponded to a sequence of characters, and detest corresponded to the following sequence of characters. And the model is what we could call like a black box meta learner. It was basically just this really huge transformer model, which essentially corresponds to different attention modules. The details on that don't matter too much, though, in terms of understanding what it's doing. And here are some results from the model. So they could do one-shot learning from dictionary definitions. So the gray text essentially corresponds to detrain, and the black text corresponds to detest for this task. So the kind of training example is to scree something is to swing a sword at it. An example of a sentence that uses the word scree is. And then what the model produces is we screeched at each other for several minutes and then went outside and ate ice cream. There's also an example of few-shot language editing, where you want to edit language from poor English usage to good English usage. And you can give it kind of all of this context as detrain. That shows it kind of examples of what it looks like to convert from poor English to good English. And you can find that it can kind of correct this sentence, which said, I'd be more than happy to work with you in another project, to I'd be more than happy to work with you on another project. And also this sentence here, which is provide me with a short brief of the design you're looking for, and that'd be nice if you could share some examples or project you did before, to please provide me with a brief description of the design you're looking for. And that would be nice if you could share some examples or projects that you have done before. So it corrects kind of the language in a few different cases. And this model is also trained on kind of tasks that we wouldn't really consider as few-shot learning tasks, which, for example, just correspond to giving it a title and a subtitle, and it can generate an article on the topic that you give it. Okay, so yeah, those are some examples of meta-learning applications and ways to formulate different problems as meta-learning problems, ranging from imitation learning, drug discovery, motion prediction, and language generation. Yeah, and then that kind of covers the goals for this lecture.
Yeah, hi, Professor Finn. So I have a question. So for the data set of omniglot, so we have different languages and different characters. So we want to perform the meta learning. So I'm wondering, so what we are trying to do in the homework is to sample. For example, if we want to do 5-way one-shot learning, we will sample 5 characters from the same language. And I'm wondering if there's any reason that we want the 5 characters to be in the same language. What I think we can also do is to shuffle all these characters across all the languages and to choose 5 characters and do the same method.
Yeah, so in the literature, people actually most frequently shuffle characters across languages, just like what you mentioned. And that's a kind of, yeah, a completely reasonable thing to do. One reason why it could make sense to not shuffle is if, for example, it's harder to discern characters from the same language than to discern characters across languages, which will kind of better prepare you for test time if you're only asked to compare characters across kind of within a language. But yeah, in general, it makes a lot of sense to shuffle across alphabets, and that essentially gives you more tasks for meta training.
Yes, so, and I also want to ask, so I think these 2 task distributions are different, right? So whether you shuffle all these.
Yep, they are different.
And so in practice, so is there any reason, for example, whether we should consider to shuffle or not shuffle?
In general, I think it makes sense to shuffle the meta training set because it essentially just gives you more tasks in addition to the tasks that you get within a language. So in general, I think that in like almost all cases, it makes sense. If you have a very large number of alphabets and you have plenty of data, then it may make sense to only consider tasks within a language, because that will be kind of a harder task that's reflective of a setting that you'll realistically see at test time. Because oftentimes with these systems, you won't be, what you care about most is like reading someone's handwriting, and you're not going to see people like writing characters in different languages most frequently. But in general, in like almost all cases, I think it makes sense to shuffle all of the characters across languages.
Yes, so if we can actually shuffle all the languages, and I'm wondering, so I think most of the data sets can be formalized into the meta-learning case, where, for example, we have different classes, and what we can do is just to sample from these different classes and to form this task distribution and perform this kind of few-shot learning task.
Yeah, that makes sense.
Okay, thank you so much.
Yeah, I'm a little confused with the dermatological disease diagnosis problem setup. So there are 150 base classes and 50 novel classes, right? So are the 50 novel classes the held out classes?
Yeah, so these 50 classes are held out from like training the prototypical clustering network and the prototypical network.
So this is like a 200-way K-short classification problem, right?
Mm-hmm. Yeah, so they held out these 50 novel classes, and then at test time they evaluated on all kind of on the full 200-way classification problem. And then these numbers are reporting kind of the 200-way classification prediction, average across base and novel classes, average across only the base classes, and average across only the novel classes.
So during the training, what is being fed to the network since you only have 150 classes?
During the training, the images from those 150 classes are passed into the network, where you basically pass it into the network, embed kind of a few examples from like 5 examples from each of the classes that you sample. You compute the embeddings, and then you take new examples from those image classes and train it such that these prototypes are accurate on those new examples for the classes that you sampled. And then at test time, given the new ones, you also additionally embed those to get additional prototypes in this learned embedding space. And then when you do classification, you look at kind of whether it predicts it for some of the existing prototypes or some of the new prototypes. Whether it's closer, like basically what prototype it's closest to.
So during training, you only feed 150 classes, right? But during test, you feed 200 classes.
Mm-hmm. Yeah, and it may be that they actually, I couldn't actually find this hyperparameter in the paper, but it could be that they actually subsample the 150 during training. They may just sample only like 50 or something, or 20 when they do this, when they kind of predict this. The downside is that meta-training and meta-testing aren't exactly matching, but it still can work reasonably well, just like how the Siamese networks worked well when you had the kind of like a one-class classification during training and an n-way classification during testing.
Thank you.
Yes, I have a quick question about the GPT-3 example.
Mm-hmm.
So you listed a few examples at test time.
Yeah.
Maybe the next slide. Yes, here. This is how the model is run at inference time. But during training time, the meta-train examples are just they split the whole sentence into 2 pieces. And the first one is the meta-train input, and the second one is the meta-train test output. And for the meta-test example, did they mask the output so that the model can predict the output?
Yeah, so different tasks correspond to basically like language generation, and so detrain might be this, and then detest is is like generating this. So it isn't fed in. This is like, you could consider this as like Y test. Actually, sorry. You could consider the black as like Y test, and this is like this is like Y train, and X is equal to nothing. So the task is to basically generate Y.
Yeah, I remember that. Oh.
Yeah, so the task is basically to generate Y train. So they're given Y train, and then the goal is to generate Y test, which corresponds to this black sentence.
I see. So there is actually no input to the model.
There's no kind of X test input. This kind of, the aggregate of X train and Y train is equal to D train, and D train is passed into the model because it's a black box model.
I see. So if they used an optimization-based meta-learning, would the setup be like similar to the language model pre-training and fine-tuning approach?
Yeah, where you would then fine-tune on like all of this if you use an optimization-based meta-learning.
I see. Cool. Thank you.
Okay, sounds good. I think that was the last question. Have a good rest of your week.